Okay, I'm going to go over step by step how to do each one of these. This first problem was already solved in a separate video, which I'll link in this in several places. But it's linked in the original assignment for sure. Okay, so now what we've got is we've slammed down our brakes while going down a hill. So I'm going to draw the incline. Okay, there's my car. Okay. We are going down the hill, so I'm going to make a little velocity vector here. But again, do not, under any circumstances, do not actually draw anything but force vectors on your free body diagram. No accelerations, no velocities, only forces. Okay, so let's see. Let's think about the different forces. All right, so do we have a weight force? Yes, we do. Straight down. All right. Is there a surface supporting it? Yes. So we're going to draw the normal force in perpendicular to that surface, which again is perpendicular to this, and that's perpendicular to that. Okay. What else? Is there an applied force? So we're skidding to a halt. There is a brake force. I'm going to call it a friction force. And the reason is when you call it a friction force, it means you get to use this formula. I just got a little bit out of here, so it's a little bit better to call it a friction force, although you could call it a brake force or a force applied. So friction forces, remember, go parallel to the surface, opposite motion. So since it's going down the hill, the friction's going to be along the hill up. Okay, we're skidding to a halt, so there is no engine force. You may not realize this, but your engine disengages when you hit the brakes. If you drive standard, you know this because you actually have to hit the clutch and disengage the engine. So you are not continuing to propel yourself forward at the same time you're braking. So we're now done with the original forces. Now, next step is to separate the weight into its components. So again, I'm going to imagine the weight is a hypotenuse of a triangle. There's my force perpendicular, and this is my force parallel. That kind of gets rid of this one. Okay. And remember, whatever this angle is will always be the same as that because it's similar triangles. Now what we're going to do is use this to write specific forms of F net equals ma. And again, we're going to do this in two directions. We're going to do it in a perpendicular direction and a parallel direction. Okay, and this is the whole point of the diagram. So looking at my picture, in the perpendicular direction, I have two forces. I have the normal force and the perpendicular component of the weight. And this does not accelerate in the perpendicular direction. They never do. So surprise, surprise, normal and perpendicular are perfectly balanced. All right, in the parallel direction, I have two forces, force friction and force parallel. Okay. And this is decelerating, so we're going to leave this alone. And we're done. We did our free body diagram. We separated it into components, and we wrote our two formulas. Let's move on to the next page. Okay. All right. A child slides down a slide, friction applies. Okay. All right, so this is the child on the slide. All right. And let's see. Is there a weight force? Yes, there is. All right. Here we go. Straight down. Nice and big. All right. Is there a normal force? Yes, because there's a surface supporting it. So I'm going to draw the normal force in perpendicular to the surface. All right. An applied force. Again, when you slide down a slide, unless you're literally pushing yourself down with an applied force, and they would have to tell you that, you're probably relying on the portion of gravity to push you down. So there's not a specific applied force because they don't mention the kid pushing themselves. There's no strings involved, so there's no tension. But there is a frictional force parallel to the surfaces in contact, opposite motion. Since the child is going down the slide, the friction's going to be up this way. Cool. So we're done with the three forces. Now we're going to separate the weight into its perpendicular and parallel components. So there's force perpendicular, here's force parallel, and that kind of gets rid of this one. Okay, so now we're going to write our specific forms of F net equals ma, one for the perpendicular direction and one for the parallel direction. Okay, so in the perpendicular direction, once again, we've got normal and force perpendicular component of the weight equals ma perpendicular. It's not accelerating. Once again, normal and perpendicular are balanced. Surprise, surprise. And then in the parallel direction, I also have two forces. I have a force friction and the parallel component of the weight. And this is accelerating. They're either accelerating or going constant velocity. So I don't know. I'm going to leave this alone. And we're done. All right. And now we have a child is dragged up a snowy hill at a constant speed. I made it backwards. So here's the child on the snowy hill. Okay. So we have a weight force straight down. We got a normal force. Okay. They're dragged up the hill. So there is an applied force going up the hill. And there is friction parallel to the motion, to the surfaces in contact, opposite motion. So those are our four forces. We're now going to separate weight into parallel and perpendicular components. So like that. Okay. There's force perpendicular. Here's force parallel. That gets rid of this. Okay. So now we're going to write specific forms of F net equals ma for the perpendicular direction and the parallel direction. So once again, in the perpendicular, I have normal and force perpendicular equals ma perpendicular, and it's not accelerating. Once again, this pretty much always is the same for inclined plane problems. In the parallel direction, I have three forces. I have a force friction, a force applied, and the parallel component of the weight. And these all add up to ma. And because the accelerator is going at a constant speed, the acceleration is 0, so this goes to there. And we have our two formulas. Okay. All right. Hope that was helpful.